When raw, unscaled data points enter a machine learning model, like a neural network, they often collide into an unstable heap. Pattern-finding algorithms struggle to calculate meaningful weights when the incoming geometric objects are sized and distributed randomly. This instability stems from the inherent noise within small samples of empirical data. The sales figures from a single store over a single week represent the high degree of random variance found in a specific, limited instance. The law of large numbers provides the mathematical framework to stabilize this variance. On a 2D scatter plot, a small number of points creates a jagged, unpredictable trajectory. As the number of data points increases into the thousands, random variance begins to cancel itself out. The noise is gradually smoothed by the volume of information. With a massive sample size, the empirical data converges towards its true theoretical probability. The trend lines become reliable. Data science manages this transition through a specific pipeline, mapping empirical data onto theoretical distributions, calculating the standard deviations, and standardizing the results with z-scores. Mathematical standardization is the mandatory prerequisite for artificial intelligence. Without it, the model simply amplifies the random noise of the sample. The first step in this pre-processing stage is visualization. In Python, a single line of code shows the initial shape of the raw dataset. This histogram represents the empirical distribution. It is a literal, finite count of a real-world sample. Because it reflects reality, the bars are often jagged and the overall shape is imperfect. These imperfections are known as skewness. Real-world data is rarely symmetrical, often containing extreme values that pull the data toward one side of the scale. In a right-skewed distribution, a few high-value outliers stretch the geometry of the histogram, creating a long, tapering tail. This tail drags the mean, the average, away from the median. Relying on this skewed average in a business context often leads to overestimating typical behavior. To create a reliable model, we abstract this messy reality. We overlay a probability density function, smoothing the jagged bars into a continuous curve. This creates a normal distribution. In this theoretical model, the mean, median, and mode all sit at the exact center. This abstraction provides a pristine framework that machine learning algorithms can interpret with mathematical precision. To measure the spread of this curve, we use the standard deviation, or sigma. This is the unit that describes how far any data point sits from the central mean. We can mark geometric boundaries at exactly one standard deviation above and below the mean, shading the central region. According to the empirical rule, 68.3% of all data in a normal distribution falls within these boundaries. Expanding to 2 standard deviations captures 95.5% of the data. At 3 standard deviations, we encompass 99.7% of the entire population. Retailers apply these percentages to physical inventory. This warehouse layout allocates 68.3% of shelf space to sizes within 1 standard deviation of the mean. Mapping inventory to central boundaries aligns physical supply with the highest mathematical probability of future demand. For the rare demographics falling outside the 2 standard deviation boundary, businesses often switch to highly targeted marketing rather than maintaining large general stock. The empirical rule allows capital and space to be allocated based on statistical reality. We are now left with the final 0.3% of the data. These are the values sitting at the extreme tips of the tails. These points are outliers. They represent anomalies that can distort a predictive model if they aren't filtered or addressed during pre-processing. This Python filter isolates those anomalies by identifying every row with a distance from the mean greater than 3 units. This logic is powered by the z-score. To find the z-score, we subtract the mean from a specific data point and divide that value by the standard deviation. This unique mathematical calculation standardizes all of our variables. It allows a model to compare disparate units, like annual salary and years of experience, on a shared scale. Consider 2 students, one with an 87 in math and another with a 59 in English. The raw scores alone do not indicate which student performed better relative to their peers. Without knowing the average score and difficulty of each test, absolute numbers lack context. By calculating the z-scores, we see their performance relative to their respective classes. The 59 in English sits at positive 0.70 standard deviations, while the 87 in math sits at only 0.46. Virat's English score sits significantly further from his class average than Babar's math score does from his. He outperformed his peers by a wider margin. Z-scores strip away arbitrary units and provide a shared scale to compare completely different datasets. This standardization is a mandatory engineering step. Converting raw measurements into Z-scores allows pattern-finding algorithms to process information effectively. Whether looking at shoe sizes, daily revenue, or heights, the raw numbering on the x-axis varies across features. Applying Z-scores forces these different distributions to align. Original units are removed, leaving a single horizontal axis measured in standard deviations. This unified state is the standard normal distribution. By setting the mean to 0 and the standard deviation to 1 for every variable, we create a universal language for the data. Algorithms calculate relationships using these standardized units, identifying patterns based on deviations from the norm. From filtering outliers to training neural networks, standardizing empirical distributions is the critical step that transforms raw descriptive data into predictive machine intelligence.